are 2604CBC.
And we are here to present to you Experiment 1, Determination of Orifice Coefficients. So what is an orifice? An orifice is an opening with a closed perimeter through which a fluid flows. The usual purpose of an orifice is the measurement or control of flow. It's usually circular, square, or rectangular in cross-section. There are three kinds of orifice coefficients: coefficient of velocity, coefficient of discharge, and coefficient of contraction. Coefficient of velocity and coefficient of discharge can be solved by dividing the actual value to its theoretical value, while for the coefficient of contraction, it happens at the vena contracta, where contraction caused by the orifice ceases.
This activity aims to obtain data on the individual character of the orifice. The first thing we need is the hydraulics bench. Secondly, we need a set of orifices. The next thing we need is the orifice and jet apparatus. Finally, the last thing we need is a stopwatch.
Set up the orifice tank. After setting up, we now start the pump. Regulate the flow rate by means of the delivery valve to maintain the water level at maximum height. Care should be taken to ensure that this level is steady. Set the needle and the profile gauge to just reach the discharge steam, and then clamp it in position. Be sure that the needle just barely touches the steam to avoid errors. Measure the horizontal distance from the orifice to the lowest needle, and the vertical distance from the orifice center line to the tip of the needle point. This step is very important because this is where you will get the data that will be used in the laboratory report. So be sure to be accurate in measuring. For the discharge, open the bench valve and drop the ball valve to measure the volume. Record the time for 1 to 3 liters and 3 to 5 liters. The last step is close the valve and switch off the pump. For more trials, just repeat the steps to obtain another set of data.
We will be presenting to you our data and results. Take for an instance our first trial in the 6mm orifice diameter. The value h equals 0.120 meters in the first column was being read from the markings on the main reservoir. The three x values were obtained by measuring the respective horizontal distances of each needle from the orifice. These were already actually given. The three y values were obtained by measuring the vertical distance of each needle point from the line of sight of the orifice, and this corresponds to each x value on the previous column. The theoretical velocity v sub t was obtained through the formula V sub t equals square root of 2gh, g being 9.81 meters per second squared and h being 0.120 meters. The resulting theoretical velocity is 2.5057 meters per second. The actual velocity V sub a was solved by using the formula V sub a equals square root of gx squared over 2y. Substitute its corresponding x and y values in the equation and we will be able to get their respective individual actual velocity. Theoretical discharge Q sub t will be solved to the formula Q sub t equals A sub t times B sub t. A sub t being the area of the orifice and B sub t being the theoretical velocity. The area of the orifice is given as pi over 4, quantity 0.006 squared meters squared. Plug in B sub t equals 2.5057 meters per second and multiplying the entire result to 1000 will give the theoretical discharge as 0.0708 meters per second. The actual discharge Q sub A is calculated to the formula Q sub A equals V over T. V being the volume and T being the time. Two raw values of the volume were retrieved and saw their corresponding time limits. These two values were 113.2 ml and 125 ml, and the time spans these volumes were reached were both 2.69 seconds. The summation of these two volumes divided by the summation of their corresponding time spans and multiplying the result to 1 over 1000 will give Q sub A a value of 0.0443 liters per second. The velocity coefficient C sub V will be solved by taking the ratio of the actual velocity V sub A to the theoretical velocity V sub T. The velocity coefficient will be 1.02. The discharge coefficient C will be calculated by taking the ratio of the actual discharge Q sub A to the theoretical discharge Q sub T. The discharge coefficient will be 0.626. The contraction coefficient will be solved by taking the ratio of the discharge coefficient C to the velocity coefficient C sub V. The contraction coefficient will therefore be 0.613.
This experiment may have had more accurate results with the absence of certain errors. The inaccurate placement of the needles on the jet is an error that may have caused discrepancies in the results of this experiment, most especially in the coefficient of velocity. This may be the cause of the coefficient of velocity not having a value less than 1. Another error that may have caused inaccuracies in the results is reading the proper measurements in the orifice and the difference in the height of the needles. The experiment was really fruitful, but one would see that all of the values of the velocity coefficients CV were barely greater than 1, ranging from 1.02 to 1.07, including those from the other group from whom we had retrieved a part of our data. The value of CV is only always between 0 to 1, and so are the other coefficients. It was observed that as h is higher, the theoretical velocities were much quicker. The values of the other coefficients with respect to each orifice were found precise enough. A few could only be seen diverging farther. For instance, the 3 mm diameter orifice had a discharge coefficient that could be probably between 0.7 to 0.8, and the 6 mm diameter ones had 0.6. There is always one standard value of each of the coefficients for each orifice.